Hi everyone. So hopefully you can see my screen at this point in time. We'll be getting started here in a couple of minutes. We got about 2 more minutes before we're supposed to start. So I started the recording. We'll just give it just a couple more minutes and then we'll go from there. Okay. Right now you should be looking at hopefully a poll everywhere poll. You can start to respond to that with questions, and as those questions populate, I'll go ahead and start to work through those. You can vote on other people's questions as well as say, hey, that's the one I want to do. So, okay, all right, so we'll start in a couple minutes, and if you are here, make sure that you go ahead and mute yourself and go ahead and not share your video either, because it will kind of slow things down. So for those of you that are just joining us, we'll go ahead and get started here in a minute or two. It's 3:02, so we'll get started here in just a second. I want to just give a little bit more time for people to show up, and also for people to start to look at this Poll Everywhere document and start, putting their questions down or saying, oh yeah, that's a question I'd like to do. So everyone should be able to respond to this. You don't have to have a Poll Everywhere account. It's pretty easy. Just go to pollev.com and /thegeek, and then you should be able to participate in this. Type your own questions. And so I'll give us 1 or 2 more minutes. And if you have joined us, go ahead and mute yourself and go ahead and also get rid of your video. That way we're not bogging down our bandwidth. Okay, well, let's go ahead and get started. We're 4 minutes past 3 o'clock, so I think that that's given enough people to go ahead and log on. I might have to go back to MS Teams and admit people into the room, so if you see me doing that, don't stress out about it too much. Hopefully all of you can see my screen at this point in time. You should be looking at a poll everywhere document that has people voting on questions that essentially they would like to see answered. You can go ahead and log on to polev.com/thegeek and submit your own question or vote on these that you'd like to see. I would like to go ahead and get through as many of these as possible. I will ask that all of you go ahead and mute yourself and go ahead and get rid of your video at this point in time, so we don't bog down things. That's not to say that you couldn't unmute yourself at some point in time and just ask a verbal question. I have no problem with that. So please go ahead and do that if you want to do that. Otherwise, you can just put your questions on this, and I'll try and get through as many of those as possible. Let me go back here. I'm hearing a lot of beeps. So okay, I think that most people are successfully in the room at this point in time. So let me go ahead and just say this, just general comments about the exam before we jump into these questions. The exam is going to take on the exact same format as the practice exam that I posted in Canvas. So that will be in the exam 1 study materials. So I would definitely advise that you, at the very minimum, look at that practice exam just to understand the format of the exam. Of course, the exam is going to be virtual, so it'll look obviously a little bit different, but the format is going to be the same. It's going to be a matching question, and then it'll be 10 what we call multiple true-false questions, and then finally 1 short answer question. Okay, and of course you're going to have all day tomorrow to go ahead and take that. So let's go ahead and come here and start working through some of our questions. I will say this, in regards to the proctoring, I don't want to answer questions about proctoring in this environment. I want to try and get through content. So if you do have questions about the proctoring and that kind of thing, please send me an email, or maybe even hang out and find some way to chat with me, and we can figure out the answers to those questions. So, okay. All right, so let's go ahead and look at this. And it looks like the top question that people are looking at here would be, could we go over the difference between standard free energy and actual free energy? Why would the standard be negative while the actual is positive? Okay, great question. This is a pretty tricky subject. So let me go ahead and come here. Hopefully you can see this and there won't be too much of a lag time. Let me come back here and make sure everyone's admitted into the room. Yep, looks like it. So come back here. Oops. Let me go ahead and admit. Oh, they got it. Okay, great. Let's go ahead and come here and look at this. So delta G versus delta G prime naught. So that's what we're looking at here. Delta G prime naught versus delta G. Okay, and what's the main difference between those, and how do we deal with those differences? And I think the question went on to say, well, when would it be a negative standard free energy or negative actual free energy, but a positive standard free energy? Okay, and so let me go ahead and just talk about this generally, and then we'll look at the specific example. The only real difference between these two concepts is really the starting point or the initial conditions for the reaction. Okay, so we can say this always, I don't think that blue is a very good color, but let's say this always begins at a 1-to-1 product reactant ratio. Okay, that's by definition our standard conditions, and that is essentially sea level, what sea level is to altitude. Okay, we begin at this, and we all just as a scientist agree that we begin at a 1-to-1 product reactant ratio. Okay, and that's our initial conditions. Okay, whereas this one is going to begin or the initial conditions are begin at Q, which is any product to reactant ratio. Okay, so that could be 1 to 1. It could be 1,000 to 1. It could be 1 to 1,000. It just really depends. And for biochemists, it would be related to then essentially the cellular conditions. Okay. Now, one of the things that I think is really helpful in understanding this difference is going to be the free energy landscapes that you've seen in quizzes and we talked about in other facets of the class. Okay, and so the free energy landscape, erase this. Free energy landscape has this kind of, or is this kind of graph where we're plotting G, not change in G, but just G, free energy, and we're plotting it versus product to reactant ratios. And I like to put right here in the middle of that graph the 1 to 1, which is of course our sea level reference point, if you will. Okay, the starting point for all standard free energy processes. Okay, so what we could do is this. Let me come back to that poll everywhere question, and it says, why would a standard be negative while actual is positive? So let's go ahead and give this an example. Okay, or we could do it the opposite way, but let's just go based off of what people are asking. So we could have a standard free energy reaction that is equal to negative 25 kilojoules per mole. Okay. Now from that, I can actually derive one thing, and that is the magnitude of the equilibrium constant. Okay. Now, how would I do that? Well, first of all, this negative sign means something to me. Okay, that negative sign, and it should hopefully mean something to you. It means that starting under our initial conditions, this reaction is spontaneous, meaning that it will produce products to reach equilibrium. Okay, that's what the negative sign always means, whether that's actual free energy or standard free energy. If it's negative, the system is going to produce products to reach equilibrium. That's the direction that it's going to go. Okay, the number itself, this just tells us essentially how far it's going to go from its initial conditions to reach that equilibrium point. Okay, so when I look at standard free energy change of negative 25 kilojoules per mole, I know this, that the reaction begins, it has to begin here at this 1 to 1 point. I also know that given this negative, that it's going to produce products to reach equilibrium. Now, I didn't put this on my axes, but this will be products, okay, here, and this would be essentially all reactants here. Okay, so as we move from left to right on our x-axis, we're getting less and less reactant and more product. Okay, so if you go all the way to the left here, starting all the way to the origin of the graph, right here, you would essentially have no products and all reactants until finally you get all the way to here. If you could theoretically get there, all the way over here to the right, you'd have all products and no reactants. Okay, all right, so coming back to this, I know I'm going to start here, the standard free energy change. I'm going to start it here, and because this is a negative, I'm going to go in this direction. Okay, so I'm going to say that this is going to end somewhere here. Okay, and I'm going to call that point KEQ because our reactions always end at equilibrium. Okay, and equilibrium is represented by some product to reactant ratio for that particular reaction. Right? And I can then draw a landscape for this. Okay? And it would look something like this. And the shape of that is somewhat arbitrary. We will say this, we have to have our minimal point at the equilibrium point, because equilibrium is where the free energy has been minimized for the reaction. Okay? And I can say that, for this reaction. Okay, that's what I can get from standard free energy. I always start at 1 to 1, and then that negative sign tells me I'm going to go to the right. Okay, 25 tells me how far. If it was negative 35, I would have drawn my KEQ closer to the product side. If it would have been negative 15, I would have drawn it closer to the reactant side because it doesn't go as far from its initial conditions. Okay. Right. Now, then the question I think in that's on Poll Everywhere says this: well, how could I have that and then a delta G that's positive? So let's say positive 10 kilojoules per mole. Okay. Well, when we look at this again, we can look at the sign on this. The sign on this tells me that starting under those conditions, the initial conditions, we are going to produce now, in this case, because it's positive, we're going to produce reactants to reach equilibrium. Okay. And then again, the magnitude here just tells me, well, how far are we away from that equilibrium point? Okay. So when I look at this then, and I say, oh, this is positive, then I'm going to say that I'm going to have to start somewhere over here. Okay, and I'm just going to pick a point, okay, that's not entirely arbitrary, but somewhat arbitrary. I'm just going to pick a point here and just say, okay, well, this is Q, okay, and that's our initial conditions, right? Again, coming back to this, that's our initial condition, meaning our initial product reactant ratio for our actual conditions. This reaction is going to produce reactants. It's going to go to the left to reach equilibrium, okay? And you can tell that by the energy chain, you know, the energy at that Q is higher here than it is at equilibrium. Is going to go down in this direction, okay? Now, if it had been positive 15, well, then I would have put it closer to the products. If it had been positive 5, then I would have put it closer to KEQ, okay? So that's how we look at that number, okay? Right, so hopefully that addresses that question. If not, by all means, again, you can just verbally interrupt me. Just, you know, put your unmute yourself and say, I don't understand that or whatever, okay? But if not, then I'll just keep on trucking on with this Poll Everywhere stuff, okay? Right. So let me get back to Poll Everywhere here. Where is it? There it is. Here we go. All right, so we just did that one. Let's do the next top one. If something is entropically driven, does this mean it will be endothermic and require energy? And also, can a reaction be both enthalpically driven and entropically driven? Good question. Okay, so I don't know if I need to necessarily draw anything with this other than just to respond to the question. Okay, the question is if something is entropically driven, does this mean it will be endothermic and require energy? Not necessarily. Okay, and this is really addressing the next question. You can have something that is exothermic and still be entropically driven. It's just that the entropy term is much larger than the enthalpy term. Okay, I'm going to really give examples of that. And generally speaking, when we talk about something being entropically driven, it does typically mean that it's endothermic, but not necessarily. Okay, something can have just a much larger, more favorable entropy term, and we can say, well, this is entropically more favorable than it is enthalpically favorable, okay, and say that. Okay, in this class, entropically driven processes will generally speaking be something that's endothermic or really have no change in delta H, okay? So for instance, after the exam, we'll go into protein folding, and we'll look at examples there where really the change in enthalpy is going to be almost zero, okay, but for a protein folding event, but it'll be quite entropically favorable, okay? So anyway, the second part of that, and also can a reaction be enthalpically driven and entropically driven? That probably not really, okay? We would say in that case, this is spontaneous and has a very favorable entropy and a very favorable enthalpy, okay, in that case. Right? How do you know what charge an amino acid has at a pH of 7? All right, so this gets to that, some of the questions that we're dealing with in regards to how do we predict the form of an amino acid at any given pH. So let's deal with that and go from there. I can say this, okay, with a great amount of certainty, okay, to just help you out and make this very simple, right? All the forms of the amino acids that you see in the textbook are the predominant form at a pH of 7. Okay, so they are drawn at a pH of 7 because the typical pH, of course, of a biological system is 7. Right? So that's the way they're drawn. I think that a good strategy for these types of questions is to go ahead and draw an amino acid in the form that it might exist at 0, and then just simply start removing protons. I found that can help students. So let me just do this, okay, and try and help you all with this connection. So I will draw here the amino acid glutamate, and I'm going to draw it as its predominant form at a pH of 7. Okay, so there's the amino acid glutamate at a pH of 7. And you say, that's awesome. How did you know that? Okay. Aside from the fact that I look at these things on a daily basis for my whole, for my whole educational career since I was a freshman in college, aside from those things, there are some strategies that you can take that are fairly straightforward, okay, to understand this. Of course, you would have to know the base structure of glutamate, okay, to do this, and that's why I've asked you to memorize the amino acids, okay? So here's what I want to do. I'm going to take the pH all the way down to 0. And the reason that I want to take it all the way down to 0 is because you can then say everything's protonated, okay, at a pH of 0. If you could get glutamate into an environment that's pH 0, then everything will be protonated. And so what glutamate will look like in that instance is going to be this. Okay, and there you go. Now I'm going to go ahead and circle here the differences between what you see here and what you see over here, just to highlight them. Okay, and this is again glutamate at pH equals 0. Okay, now when we consider glutamate, and these values will be given to you, they'd have to be given to you, okay, to solve these type of problems. But when we look at a pK, or the pKs of glutamate, we have pK1, and this is going to equal, or it's about equal to 2. Okay, I'm not sure exactly what it is. I didn't memorize it. So it's about equal to 2. Okay, and then there's a pK2 that will be about equal to 9. And then there's a pKr that is going to be, and I for some reason have this memorized, 4.65. Okay, so that's the pKr. Right, so pKs, pK1 is for this group, pK2 is for this group, and pKr is for this group. Right? Now, when you look at the concepts covered in Chapter 2, and also in Chapter 4, and then even the summary and reflection question in Chapter 2, you can derive a fairly simple rule using pK and pHs. Okay, and that rule is essentially this, that anytime the pH is below a pK, that group is predominantly protonated. Okay, so when you go to a pH of 0, then this is why I say we can draw all things protonated, because at a pH of 0, I'm at a pH that is below all 3 of my pKs. Okay, and that then means that those are going to be protonated forms of those functional groups. Okay, now as you then start to move up in pH scale, as you would in a titration curve, then you are going to start to remove protons, or you're going to quote unquote titrate certain functional groups. And by titrate means that we're just going to take the protons off of them. Okay, so if we were to go to a pH of 3 or 4, okay, then what happens is that we surpass pK1. Okay, let me just real quick check and make sure everyone's getting in. Here we go. Oh, he left. Okay, so come back here. Okay, so so let's say we go to a pH of 3. Okay, well, we have now gone past the pK here, and now we're getting into the land where that functional group has been predominantly titrated. We've removed the proton because the pK represents the pH in which 50% of the functional group is protonated and 50% is deprotonated. So at a pH of 3, we're above pK1, and therefore we can say that our alpha carboxyl group would be deprotonated. In fact, I could draw it like this. The side chain would remain protonated because we haven't, at a pH of 3, surpassed the pKr. But the alpha carboxyl group here at a pH of 3 would have been, the pK1 has been surpassed. So this would be then glue at pH 3. Okay, so the question that we all looked at on Poll Everywhere, let's go back to that environment, says this: how do you know the charge an amino acid has at a pH of 7? Well, let's come back here. Okay, we've already drawn this up. At a pH of 7, we have surpassed both the pK1 and the pKr. And notice what we've done here. We have deprotonated our 2 carboxyl groups, one on the side chain, one on the alpha carboxyl group. Okay. However, this, the alpha amino group, because at a pH of 7 we haven't surpassed the pK2, we leave that protonated. Okay. And again, this is all relative to what we had at a pH of 0 when we had everything protonated. Okay. Now I can then look at this. If going back to fully answer the question, it says, well, how do I know the charge? Well, this is probably the easiest part, right? -1 is -1 plus another -1 is -2 plus 1 is a -1 overall charge. Okay. All right. So hopefully that strategy can help you out understanding when to take protons on and off of things. Okay. Biggest thing is just to remember, okay, as we lower pH, we're protonating things, okay? And the pKs just simply represent the place where we're entering a landmark for that particular functional group, okay? Because right at that pK, the pH right at that pK, we're at 50-50 protonated, deprotonated mix, okay? All right, I keep hearing a bunch of beeping, so I'm gonna admit some people. There we go, okay. All right, so let's come back to now Poll Everywhere. Where is it? There it is. Okay. And again, if you have questions, if you want me to go back to that, you can just unmute yourself and respond in that way. So if you want to do that, okay? All right. Or just, write a new question. All right. How do you know what charged amino acid at pH 7? We already done that one. Titration graph. Okay, so this is right along with what we were just doing. Okay, I could have drawn a titration graph, so let's go ahead and do a titration curve or graph of glutamate. Okay, so with this, I'm going to go ahead and draw my axes here. And everything that we've done in this class, and the only thing I really care that you'll be able to do is essentially the titration of like amino acid or another weak acid with a strong base, hydroxide. So we're going to do pH versus hydroxide added. And this would be hydroxide equivalents added. Okay. And so essentially what you do here with these titration graphs is, again, you start at very low pH, okay, and then you work your way up. Okay, and if you remember the titration experiment, we would essentially put glutamate into a beaker, and we would take the pH of glutamate, okay, and we would try and put the pH really low for glutamate, and we put that in the beaker, and then we start to drop hydroxide in it, and we monitor pH. Okay, what we would get is something that looked like this, or each little dot would represent one pH reading. Getting no, okay, great. So let's go back here. There we go. So each of these represents a pH reading. Okay, now some of you really, I would imagine the question is in regards to, well, how do you know, right, that a pH, short of doing the experiment yourself, how would you know how to draw one of these graphs? Okay, well, each one of these pKs represents a point in which there's a leveling off in terms of the change of pH. Okay, so I know that this graph, because it's a graph of glutamate's titration, is going to have 3 points where it's going to level off. And then I go way up here, this is going to be way, way, way up. And then this will go up like that. Okay, all right, so that would be the titration curve of glutamate. Now, what do those leveling off points mean? Well, each of these leveling off points, I could draw a little dot in the center of them, and that would be essentially the equivalence point or the midpoint for the titration of that functional group. Okay, and at the equivalence point or the midpoint for the titration of that functional group, okay, we are at the pH that's equal to the pK. So for instance, pK1 is 2.0, okay, and I know that at the midpoint, right, of glutamate's titration of its alpha carboxyl group, we're going to be at a pH of 2.0 or about, because pK1, again, I haven't memorized what the pK1 is for that, but it'll be about 2.0. And right there, at that pH, we're essentially in a form where 50% of the molecules have that form of the alpha carboxyl group, and 50% of the molecules would have that form of the alpha carboxyl group. Okay, so if I had 100 glutamate amino acids in my beaker, 50% of them would have COOH, and 50% of them would have COO minus at the alpha carboxyl group. Okay, now as we then progress away from the titration of that, so we're going in this direction, and we're going up in pH, we're now predominantly deprotonated alpha carboxyl group, and now we're approaching the midpoint or the equivalence point of the titration of the side chain, which is essentially right here. So I could draw a line over here, and this would be 4.65 pH. And at a pH of 4.65, 50% of the molecules would have a carboxyl group on the side chain that is protonated, and 50% would have it deprotonated, as we see over here on the left. Okay, right, and then we'll go further up the graph. Okay, as we get further from that midpoint, then the predominant form, right, greater than 50%, will be the one with a deprotonated alpha carboxyl group and a deprotonated side chain. Okay, and then we just keep going. Now, incidentally, just so we make our connection to our last question, pH is 7. That's going to be essentially probably right here, given the way I've drawn this graph. Okay, which means I have passed this midpoint, I've passed this midpoint, but I haven't passed the midpoint up there, which means that I have the deprotonated alpha carboxyl group, I have the deprotonated side chain, but I have a protonated alpha amino group. Okay. Now, as I approach that alpha amino group coming this way, once I reach here, and this would be at a pH of around 9, whatever our pK is, then our alpha amino group will take on the form of NH2. And so I could draw the whole amino acid as such. this would be the predominant form of glutamate at pH greater than 9.0. Okay, where 9.0 represents our midpoint here. If it was at 9, then we'd have to say that, well, 50% of them have this, and 50% of them have this. Okay, right. So that's the titration curve. The titration curve, I think, is a really helpful and visual way to try and understand how do we predict the charge of an amino acid at any given pH, given pKs. You have to be given pKs. Okay. Right. So if there are remaining questions on that, again, interrupt me, unmute yourself, ask me, or submit more questions below everywhere. Okay. All right. Explain why question 19 is false. Okay, so we're at 3:35, so we still got about 25 minutes, so we can keep working our way through this. So question 19, I'm going to assume that's question 19 on the practice exam. And so I'm going to pull up the practice exam.
Excuse me?
Yes. Yes.
I just wanted to point out the student typed in the messages that they wanted to see explanations of the titration graph on the practice exam and the questions related to it.
Oh, okay. So I went through that whole thing. Okay, thank you for pointing that out. So let me go back to that before we get to question 19. So I missed that on that. So this is on the practice exam. This one, we're looking at this one. Although that's good because the titration curve is the exact one that I drew. Okay.
It looked pretty similar too. I just wanted to let you know.
Yeah, so thank you for letting me know that. So let's go ahead and go through this, though. We might as well we'll do this since we've built the foundation to understand these questions now. So this one, the PKs are given there. So I was kind of right. The PK1 of glutamate is actually 2.19 and 9.67. And I said that I had memorized this and I had forgotten. I was wrong. So I got to give myself red check minus. Red check minus, or this is a blue check minus. And that is that this should be 4.25. Sorry, I said 4.65, so I was wrong. Okay, so it's 4.25. Okay, so come back to this. A blue check minus. That's a first for me, I think. So anyway, so we can come back to this and we can actually look at this now. So based on the following graph, which statement is R correct? All right, it says the graph represents the titration of an amino acid that falls in the positively charged R groups, okay, or it would have a positively charged R group. So, so this PKR, again, you would want to look at that and say, okay, PKRs, let me go to the top of the test and find a PKR, oh, that's 4.25, that's glutamate, and hopefully from that you know that, okay, this is an acidic side chain. Acidic side chains are never positively charged side chains. So this would be a negatively charged side chain, so I would say that that would be false, okay, based off of that, okay. The charge on the amino acid of the side chain at a pH is, the charge on the amino acid side chain at pH 6 is -1. Well, let's go back here, okay. We would be at a pH of 6, okay, right here, and we are above that PKR, 4.25, or we could even go back to the exam, right, somewhere around here, where would we be? Let's get a red pen. Right there, we are above that PKR, and so this would be a -1 charge. So yeah, I would say predominantly that would be a true statement, okay? And that would be for the side chain, okay? And it says the charge in the amino acid at a pH of 6 is equal to -1. So this would be the whole amino acid, and that would be true as well. So the form that we'd be looking at would be essentially the same form that you would see at a pH of 7. Okay, so you add these up, and this is a -1. Okay, so +1 -1 is 0, plus an add of the -1 is -1. Okay. Let's see here. The amino acid is aspartate, so again, the only way to know that would be to just look at the PKR. Okay, and this is where I got screwed up. The PKR of aspartate is 3.65. So if you go back here, it's 3.65. It's aspartate. And I said 4.65, and so I screwed those two up. But anyway, so it's not aspartate, it's glutamate, because it has the PKR. Okay, and then finally, the predominant form of the amino acid has a side chain that has a +1 charge at pHs below 4. Okay, and that would be false too. So that side chain, the protonated form of glutamate, come back here. Side chain will never have a +1 charge. It will always be neutral. Okay, so thank you for pointing that out and interrupting me. Let's go ahead and I forgot that there's these chat functions. So okay, so there we go. Okay, so now so the next one, explain why question 19 is false. Okay, let's go ahead and look at that one, and I'm again going to assume that what we mean is 19 on this practice exam. Okay, all right, so let's look at this. It says the reaction B goes to C has a standard free energy change of -20 at 25 degrees Celsius. Starting under standard conditions, one conclude that. Okay, so real quickly, this is the only information I have. Okay, about the reaction. And what I can tell from this reaction is essentially this. Let me go back to, I've lost the ability to control my screen here for some reason. That's not good, because I can't even read it. Technical difficulties. So just give me a moment, because I can't even get back to Teams right now to do anything. So, so hang with me for a little bit. I'll get to that question here in a little bit. Okay, there we go. I think that I can do this. So let's come back here. Okay. So coming back to, there we are. So let's come back to this. Okay. If you remember what I was talking about when I was mentioning this at the very beginning of our Q&A here, we looked at standard for energy change, and I said, okay, standard for energy change means we're always going to start here. And if we have a negative sign on that, then we are going to produce products to reach equilibrium. So essentially, the same things I can conclude from -25, I can conclude for -20. And that is that my equilibrium is going to go to the right. We're going to produce products to reach equilibrium starting under standard conditions. I can't say anything about actual conditions because I don't have any information on actual conditions in the question. So let's go to 19. The delta G for the reaction will be negative. So I can't say that because I don't have a Q value. So that's why it's false, because the Q value could be something like this. It could be this over here. And if that's true, then it would be positive. Okay. And you just don't have that information, so you have to say false. Okay. So that's why. All right. Okay. Let's look at this one. Learning objective number 4. What are the effects that non-covalent interactions will have on enthalpy, entropy, and the free energy of a system? How do these concepts apply to biological structures and interactions? So what I would be hoping that a student would be able to do in learning objective number 9 is to be able to predict something like, okay, we have a protein and it's got an ionic bond between the aspartate and a lysine side chain in its tertiary structure. If the protein is mutated to have an aspartate, to mutate that lysine in the lysine aspartate ionic bond, and that lysine is mutated to a glutamate, what will that do to the enthalpy and the free energy of the system? So in that case, right, what we go from is an ionic bond, we lose an ionic bond, and we would go to something more of a repulsion. Okay, so the enthalpy would no longer maybe be negative in that case, but it would be possibly positive, and that would then cause the free energy of the system to possibly be positive, possibly, okay, because we're getting an unfavorable enthalpic term. Okay, so that's kind of what I'm looking for. That's the second part of it. How do these concepts apply to biological structures and interactions? Okay, entropy, right? This would be the introduction of, let's say, a non-polar side chain on the exterior of a protein. What is that going to do to that protein's entropy? Okay, well, by putting a non-polar side chain on the exterior of a protein, that would then cause the entropy to actually decrease, okay, because that non-polar side chain would interact with water in an unfavorable way, and that water entropy would decrease, okay? So those are the types of things that I'm hoping you would understand when we look at non-covalent interactions. The things that we've certainly talked about in class, right? I mean, enthalpy can be very straightforward, boiled down to a very simple concept, and that is that changes in enthalpy equal change in H bonds broken minus H bonds formed, right? So when you start to look at biological structures, okay, like a protein or something like that, we're thinking about, well, what are the bonds that are being broken to form that structure, and what are the bonds that are being formed to form that structure? And how is that going to relate then to changes in enthalpy? Generally speaking, if we have more bonds formed or stronger bonds formed at our final conditions relative to our initial conditions, then versus the amount of bonds broken going from initial to final conditions, then we are going to have a negative change in enthalpy, and that's favorable. Okay, generally speaking, when we start to think about entropy, at least in this class, we've really applied that concept almost exclusively to the hydrophobic effect and the effect of water entropy when exposed to non-polar regions of some molecule. Okay, so those are the things that I'm looking for you to bring forward. Okay, okay. Again, if you have interruptions, just like the last student interrupted me, please go for it and let's interrupt me. Okay. All right. What destabilizes alpha helical structure? So questions 46 through 50 on the exam. So let's go ahead and look at that. Okay. Let me jump back to that Teams. Yes, 19 on the exam. Okay, great. So we got that. And let's go back to here. And let's not there. I'm going to look at the exam. What questions were we looking at? 46 through 50. Great. Okay. Okay, so an alpha helix would be destabilized by. Okay, so let me just, before I even look at 46 through 50, let me just, generally speaking, talk about the things that could destabilize or stabilize alpha helical structure. Okay, so first, stabilization. Right? Anytime an alpha helix will form, the primary driving force for that formation is going to be the formation of hydrogen bonds in the backbone. Right, so that's what primarily stabilizes an alpha helix. Okay, so we then look at, as we look at things that could destabilize that. This would be things that would disrupt those hydrogen bonds, okay? And there are several things that we talked about in class that can disrupt those hydrogen bonds. Okay? And by the way, with beta sheets, the primary driving force for the formation of those is also going to be the formation of backbone hydrogen bonds, okay? All right, but going back to alpha helix, okay? So let's think about the things that, from a side chain standpoint, can disrupt those hydrogen bonds. Okay, first of all, the introduction of a proline. Okay, so prolines, when you introduce a proline, the amide nitrogen of proline in a peptide lacks the hydrogen bond donor, okay, the hydrogen coming off of that nitrogen. So in the Echo 360 recording, I drew what proline structure would look like, and I demonstrated this won't have a hydrogen. So that will start to disrupt, obviously, hydrogen bonds that will hold the alpha helix together. Not only that, but the phi and psi angles for a proline are just bad for alpha helical structure formation. Okay, so that can destabilize it. The introduction of short hydrophilic side chains can destabilize those hydrogen bonds. Short hydrophilic, okay, if you remember our discussion on that, these would be things like serine. Okay, so if we were to draw a serine, I can actually draw it right here. So serine side chain would be this. that would be short and hydrophilic. Our alpha carbon would be right there. Okay. Short, it's only got a single carbon that then has a hydroxyl group coming off of it. And what that does is it packs a very polar group right around the backbone of the helix. Well, that polar group can destabilize hydrogen bonds. Okay, if you remember, hydrogen bonds are weaker in polar environments than they are in non-polar environments. Okay, so this here, let's use a different color that's a little bit more contrasting. That here is providing a polar environment that's really close to that backbone of a alpha helix, and that can destabilize the hydrogen bonds. Okay, so that will be something else. And then finally, the last thing to consider would be, well, side chains that would interact with each other in destabilizing ways. Okay, and side chains that interact with each other are going to be 3 or 4 away from each other in the primary structure. Okay, so for instance, the second amino acid in a alpha helix will interact with the 5th and the 6th amino acid in an alpha helix. And the question would be, well, are those going to be stabilizing or destabilizing interactions? Obviously, destabilizing interactions would be things like ionic repulsions or side chains that are too bulky that they would run into each other, though we didn't talk about that, so I wouldn't expect you to recognize something like that, but we did talk about repulsions. Okay, things that would stabilize that would be formation of hydrogen bonds or hydrophobic effects or ionic bonds. Okay, so now that we've got that laid, let's go ahead and look at these questions. Number 46. An alpha helix would be destabilized, so we're looking for things that destabilize it. Interactions between aspartate and arginine residues 3 amino acids from each other. Well, aspartate is a negatively charged side chain. Arginine is a positively charged side chain, assuming that we're at a pH of 7, which I will give myself a red check minus for this question. It should say, assume you're at a pH of 7. If it doesn't, and I think the exam will, okay, because I'm really careful about that, but if it doesn't, assume you're at a pH of 7, and then blame me. Say, you said to assume it, and then we'll give you the point. Okay, but anyway, so negative and the positive, so 3 amino acids apart, they are going to interact, but they're going to interact favorably, so that would be false. 47, the introduction of a proline residue in the middle of the helix, we've talked about that in my introduction to the question, so yes, that's going to be true, that will destabilize. Long stretches of short non-polar side chains. Non-polar side chains, that's fine, right? So non-polar side chain would be something where, you know, like leucine or valine or isoleucine or something like that. Well, that's going to put a hydrophobic spin on the backbone, and that's going to make those hydrogen bonds even stronger. So this is definitely not going to destabilize, it will stabilize. So 48 would be false. Interactions between aspartate and glutamate residues 4 amino acids apart. Again, if pH is 7, yes. Okay, so because aspartate is negative charge, glutamate is negative charge, and those will repel each other. So that would be true. And then finally, 2 lysine residues in a row in a primary structure. Well, those are only one apart from each other, and those side chains just aren't going to interact with each other. Okay, so so hopefully that clears up that question for the people that were wondering about it. Okay. Okay. Rotation around the bond for question 56 through 60. Okay. We get back here, make sure I'm not missing anything in teams. Nope, not missing anything in teams. Okay. Okay, so number 56 through 60 on the practice exam. Oh yes, this is a fun one. Okay, so the figure below is that of a bond between 2 amino acids. Which of the following statements is or are true? Okay, okay, so let's look at this. We are looking at, when we talk about phi and psi angles, we're looking at this one, and we're looking at this, on the way this is drawn. Okay, so this would be the C to C. This would be a psi angle that's changing here, right? And then this one would be over here. This would be from N to C alpha. This would be a phi angle. Okay, just so we are certain of that. That would make this, right, the peptide bond. Okay, all right, so let's go ahead and look at this. Rotation around CN. So they're talking about this is restricted due to partial double bond character. No. So that's not true. Okay. The question might, as I'm looking at this, some of you might be saying, well, how do I know he's not talking about this one? Okay. So this is a great opportunity for me to say this because you're not going to be in class with me taking the exam. If there's a question like that and you feel like, well, how do I know this? Okay. There's comment sections on Canvas. Write out your comments because I have to grade these. Write out your comments and say number blah, 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 right? I thought this. Is that what you're doing? And then I will look at it. And if it's something like this where you're like, where I can look at it and say, oh yeah, I can see what you're saying, then I'll take into consideration how you're interpreting the question and grade it that way. Okay. So just keep that in mind. Okay. You have ways to comment with me. Okay. All right. So, so anyway, this one, right, is not restricted because of partial double blind character. Okay. And if it's this one that is talking about, then this is restricted because of partial double blind character. Awesome. Why did I just go all the way down? That wasn't what I wanted to do. There we go. Okay. So, so that's a tricky one. That's probably a bad question. Okay. And we'll probably want to throw that one out. Okay. Now this, oh, actually, if I had read a little bit further, it says C alpha at the end. So this does mean, so now this is more specific. This does mean, yeah, it means this one. Okay, so that's true because it's C to N is restricted to these partial double bond character, and that's right. So that should be true. Okay, now this one says the C alpha at the end. Let me go ahead and erase all this junk. That is referring to this one. Is free to rotate, and its torsion angle is referred to as the phi angle. Okay, and that is the phi angle is free to rotate. Yeah, and so that's a true statement. Okay, it's the alpha carbon is sp3 hybridized, and then I can rotate. Okay, and that is the phi angle. And then the next one says the C alpha C bond. That's this one that this is talking about. Is free to rotate, and torsion angle is referred to as the psi angle. That's right. Okay, that is the psi angle. Okay, and then finally, rotation, or the last two, rotation about the C alpha C is unrestricted, and the rotation around the C alpha N is unrestricted. And those are your key terms there. It is not unrestricted. It is restricted. Okay, and that's what the Ramachandran plot tells us. The Ramachandran plot really shows the restrictions for those because there are some of those angles that could be adopted that will cause like R groups to run into oxygens or other things on the backbone that just aren't allowed. And so that's what we'd be thinking about there. Okay, so those are both false because it says unrestricted. Now if it says they're restricted, then you say true. So, okay. Okay, hopefully that gets to that. Okay, so I'm going to do, let me answer one more of these because it's almost 4 o'clock. It's 3:57. So let me try and look over this. We'll go over the free response on the practice exam. Okay, so that's 4 people that have said, let's do that. So let's try and do this in short order. Oh gosh, yeah, so this is a fun one. So a ligand binding protein undergoes a genetic point mutation, changing a ligand binding side chain from a lysine to an alanine. The mutation results in a tenfold decrease in the binding between protein and its ligand. Okay, awesome. Okay, a mutation of the same lysine to glutamate results in a 1,000-fold decrease in binding between the protein and its ligand. Interestingly, binding to ligand can be partially restored if pH of the surrounding solution is dropped to 4 in the GLUT mutation. What do these data tell us about the interaction between the protein and its ligand? Okay, and explain why the drop in pH is going to affect it this way. Okay, so it says that we've got in our native protein, our unmutated protein, we've got this lysine side chain. And you all say, awesome. Lysine is my favorite amino acid, so I know already what you're going to draw, but go ahead and do it anyway. So I'm going to do it. All right, so here's lysine side chain. And it's okay if you have a favorite amino acid. That's fine. I have my favorite molecules and amino acids. Okay. right? So lysine is that side chain. Okay, so it's saying that there's a mutation that disrupts binding between protein and a ligand. Now, protein and a ligand may mean meaning small molecule, okay, just some small molecule. And if you do that, oh, I erased way too much, then there's this tenfold drop in binding, okay, meaning that the interaction between the small molecule or the ligand and the protein decreases. It's just not as good, okay? Now, the next one says this, let's go in this direction, that if we go from that to glutamate, man, we're just doing something terrible to it. Okay, in that case, there's a huge drop, right? So this is glue, right? There's this huge drop in binding between the protein and its ligand. All right, now, notice what we have here. Positive here, nothing, right? And then we have a negative charge way out here, okay? Now, the last piece of data, so there's even more data. The last piece of data says, oh, we can drop this to a pH of 4. Well, remember, pKr of glutamate is 4.25. And if we drop it to a pH of 4, then that means that this is going to be predominantly protonated, which means that our glutamate is going to take on this form. My handwriting got really sloppy there, sorry. There we go. So that's at a pH of 4. And I'm only drawing the side chains, by the way. Some of you are like, what? Like, this doesn't look right. I'm only drawing side chains. So the rest of the protein is implied by this, okay? All right, so, and we can restore some of the binding by doing this. Okay, so it says, what did these data tell us about the interaction between the protein and its ligand? Well, isn't it reasonable to think that the ligand looks something like this, whatever it is, to draw it, there's our small molecule, has a negative charge, and there's this nice interaction between those two. Put that molecule over here, it won't look like exactly the same, but now I'm missing that interaction. No interaction there. Put it here, okay, and now, oh, this is really bad. These, like, you know, we'll use red. Red meaning bad. I mean, they're bouncing off of each other. They're repelling one another. Okay, and then finally, this last one here. Okay, I won't draw it because I don't have a place to draw it. But if we put this and remove that negative charge and put a hydrogen there, then we lose that repulsion and we can restore some of the binding. Okay, so it's reasonable to answer the question, explain why, or it's reasonable to think that there's an ionic bond between the protein and the ligand, and that the drop in pH, okay, with the glutamate mutation restores the binding because you lose repulsion between the negatively charged side chain and the ligand. Okay, so that's essentially how you work through this. Now, interestingly, when we come back to this, okay, that's a great example of this question, learning objective number 9, okay? Because we could then put this all in enthalpy terms, and we can say, okay, well, we have, right, this would be exothermic, negative delta H, right? We lose that, right? The bonds formed are not nearly as strong anymore. And here we bond repelling one another. And so our delta H is like positive in this case. So, so we can put that in those terms as well, okay? All right, so that's going to be it, I think. So I hope that that gets us through the majority of your questions. If you have anything else that you will need to ask me, go ahead and send me an email, and we can go from there, okay? So I will tell you this right now. I'll just preface all this. Tomorrow is going to be a very busy day for me from an email standpoint, okay? Anytime students are taking virtual tests, I get a lot of emails. So be patient with my responses. I'm going to try and get through them as quickly as possible. Also, I would probably advise not doing Canvas messaging, because Canvas messaging on days like this really gets bogged down. And I start getting those messages way later than they were sent. So I would send emails directly from one of your email accounts to my aaron.shoulders@colostate.edu. email address, which is found in the syllabus. Okay. All right. So take care. Good luck on the exam. You can do this. You can rock it. Okay. And we'll see you. Well, I don't. For some of you, I'm not going to see you at all. So, but good luck. Okay. All right. Take care.
Thanks, Scott.
No problem. Of course.